Okay, now I want to talk about the Z transform at a very high level. So this is a deep subject. I could spend as much time or more than I have on Fourier, but I just want to give you a taste of it. You could do a lot with Fourier, but remember there's a couple downsides. So when I look at the discrete Fourier transform, I remember that it's actually assuming that I'm repeating infinitely. So if I cut myself off and I happen not to have gone through an integer number of periods in my window, I'm in trouble and I got all this frequency bleed. I don't really, like somehow my frequency is in between two frequency bins and that causes me to bleed into other ones nearby. So this isn't really the best representation of this. And so if I want to understand the effect of a filter, like when I convolve with something, that filter may also affect frequencies that are kind of in the middle. And so I want to know how that filter affects not just the frequency bins that I can see in the Fourier transform, but really any frequency. I want to think of all the real numbers between in this range here. I don't just want to be stuck at integer frequency indices. So the Z transform comes in to fill that void. So let me start by talking about just the low-pass filter that I mentioned before. So, let me first say I had this equation for the convolution, right? And I said, as an example, let's suppose that H0 is 1 and H of 1 is 1. So this is a very simple low-pass filter. It's only going to preserve low frequencies when I do the convolution. Now I can write that as saying, okay, so the output y of n, if I just plug in this equation here, what I can say is that y of n is equal to x of n plus x of n minus 1. That's what happens when I plug into the equation. So we call this a difference equation. It's kind of the discrete analogy of a differential equation. So I'm saying I want y of n to be the sum of x n and x lagged behind by one sample. Okay. Now here's what I'm going to do. Again, I could take the Fourier transform of this. I could zero pad it to get more frequencies. But there's a more natural way to analyze what this does to all frequencies. So what I'm going to do is just pretend I'm going to make xn be just an arbitrary phasor. Okay, so I'll say make xn be e to the I 2 pi f t. Or no, let me say 2 pi fn. So let me you have to make this in terms of my discrete time index. Okay, so let's just make x and that and see what happens. Now, I'm going to use a shorthand. So we actually say, so this is actually called z, by the way. They refer to the phasors as z. That's why it's called the Z transform. So any phasor, this f can be anything. But I'm going to use a shorthand, which is commonly used. It's going to make it much less tedious to write my equations. I'm actually going to say let omega be 2 pi f. This is called a radian frequency instead of. So this frequency is expressed in cycles. So where f is in cycles per sample. So we know because of aliasing that, so f is in cycles per sample, and we know because of aliasing that the max f can be is a half. You can't go more than a half of a cycle in one sample, otherwise you alias. What this means is that, for omega, I consider omega also less than or equal to 2 pi times that, which is pi. Okay. All right. So anyway, these are the constraints. So I'll just say, plug in. So we say z is equal to e to the I omega n. Okay. That's what we plug in for x. We plug in this thing called z. All right. So if I plug that into the equation here, what I get is, so I had yn is equal to xn plus xn minus 1. So let me just plug in e to the I omega n, and what I'll get is yn is equal to e to the I omega n plus e to the I omega quantity n minus 1. Okay, so that's what I get when I plug this in. And actually I can do something interesting where I use rules of exponents. I can factor out this e to the I omega n, and what I'm left with is y of n is equal to, let me factor, the common term, e to the I omega n times 1 plus e to the negative I. And that's it. Oh no, sorry, negative I omega. There we go. So I just factored out this common term of e to the I omega n. So I didn't mean to have two pluses there, just one plus. Okay, so here is my equation for what the output is going to be, given that my input is this phasor, where again, omega is a real number. It doesn't have to coincide with any integer number of cycles over some interval. So omega is completely arbitrary. All right, now here's where I have to use a trick. If I want to understand, so this is a complex number. I'd like to break it apart into an amplitude and a phase. So I want to break this apart into an amplitude and a phase, and I want to look at the amplitude first to figure out, to verify that this promotes low frequencies. So that's my goal. So what I do is I'm just going to use an algebraic trick. I'm going to multiply by a fancy 1. So use a trick where I multiply by a fancy 1, which in this case is going to be something over something over that same thing. I'm going to multiply this equation by e to the I omega over 2 over e to the I omega over 2. Okay, so I want to multiply the equation by this. And so I don't change it, right? This is 1. It's a very fancy 1. So when I do that, I end up getting y of n is equal to, this doesn't change on the outside, but on the inside, let me distribute this through. I get e to the I omega over 2 plus e to the negative I omega over 2 if I distribute this through, divided by, so it's actually going to be divided by the one at the bottom. So let me set that up as a fraction. So then divided by e to the I omega over 2. So let's look at that. I didn't like that. Hang on, what did I do wrong? Fraction. I needed to end the fraction. Okay. So here is the equation that I get. All right. So this I can distribute over to the other side and cancel this out up here. So I can just simplify this a little bit and write this as yn equals, I can take this out here, to cancel it out from the numerator to the denominator. I get e to the I omega n over 2 times just what was in the numerator there. So I can get rid of the fraction. Okay, so let me work with this now. So here's where I use an interesting fact. If you remember, e to the I theta, so, or just e to the I x, let me just use x, is equal to cosine of x plus I sine of x, right? what this means is also that e to the ix plus e to the negative ix is equal to, if you look at it, well, cosine is an even function and sine is an odd function. So I would get cosine of x plus I times sine x plus cosine of negative x plus I sine negative x. Actually, cosine of x is the same as cosine of negative x because cosine is an even function, the sine is an odd function. So this simplifies to 2 cosine x. Okay, so here's a little identity that I have, a little relationship between complex exponentials and just a regular cosine. So if I apply this formula, what I can see is I can write this as y of n is equal to this thing, which I can't do anything about this, but I can change this into something a little simpler, which is simply cosine of 2 cosine of omega over 2. Okay, that is pretty interesting. So, and let me just make that nicer, put the 2 over on the side here. Okay. All right, so now I've got an equation where I can clearly see, actually let me back the 2 back up here because I can see, okay, I could clearly see a separation between phase, here's my complex number which represents the phase, and amplitude. So here's my expression for the amplitude. So I told you omega is supposed to be between, is supposed to be less than or equal to pi. I can go ahead and put this back in terms of the frequency again. I can say that, frequency in terms of samples per cycle. I can say that y of n is e to the I 2 pi f n over 2, which is just I pi f times 2 cosine of pi f. So that's my equation in terms of the frequency. So if I go to plot just the amplitude part, so let's make the frequency, it's supposed to go, it never goes above a half. So I'll go from 0 to a half, and maybe I'll take like 1,000 samples. I'm going to take a bunch of frequencies in there and plot them. And so I'll say the amplitude is equal to 2 times the cosine of pi times f. Well, if I plot this, what I get is I can see that at lower frequencies, frequencies that don't go through as many cycles per sample, I have a higher response than I do at higher frequencies. So that's the essence of why this ends up being a low-pass filter. Okay, so I just want you to take that in for a second. And then I'm going to move on to an example where we add more than just a single lag here, where we add a bunch of lags. Okay, but this is the foundation. So take it in.